All right, let's jump right in. Today, we're talking about a piece of math that, believe it or not, was born from this really bitter personal feud. And now, well, now it powers some of the biggest, most influential tech in our lives. I know, it sounds like the start of a really weird joke, right? Shuffling cards, nuclear bombs, and Google, what could they possibly have in common? But it turns out there's this one single, incredibly powerful mathematical idea that ties them all together. And the story starts over 100 years ago in Russia with this furious argument about free will, of all things. So to really get this, we've got to rewind the clock. Picture this. It's 1905. Russia is in total turmoil. You've got socialist groups rising up against the Tsar. And this massive political divide, it wasn't just in the streets. It seeped into everything, even the super abstract world of mathematics. And right at the heart of this whole thing are these two guys. On one side, you have Pavel Nekrasov. He's on the Tsar's side, deeply religious, and he truly believed math was a way to prove the existence of God and free will. And his rival? Andrei Markov, a total opposite. He was a fierce atheist, a socialist, and he was convinced that math had to be pure, rigorous, and completely separate from all that religious or philosophical stuff. And the battleground for their feud? A core concept in probability. Okay, so what they were fighting about is something called the law of large numbers. You've probably seen it in action. It's the reason why if you flip a coin 1,000 times, you're going to get super close to 50-50 heads and tails. Now, the key word here, and this is super important, is independent. For literally 200 years, mathematicians just assumed this law only worked for things like coin flips, where one flip has zero effect on the next. But then Nekrasov comes along and makes this really wild claim. So Nekrasov looks at all this social data, marriage rates, crime stats, and he sees that these numbers are weirdly stable year after year. They seem to follow that law of large numbers. So he makes this logical leap. He says, hey, if the results follow the law, then the things causing them, all those individual human decisions to get married or commit a crime, they must be independent. For him, this was it. This was mathematical proof of free will. And Markov, he thought this was absolutely ridiculous, just complete nonsense. So Markov is furious. He is dead set on proving Nekrasov wrong. And to do that, he had to find a system where events were obviously, clearly dependent, where one thing directly influences the next, but the whole system still followed the law of large numbers. A real challenge. And where did he find his perfect test case? Of all places, Russian poetry. Yep, he literally took the first 20,000 letters from a famous poem by Alexander Pushkin. Now, why text? Well, think about it. In any language, the letter you're about to write is super dependent on the one you just wrote. Like how a Q is almost always followed by a U. These letters are the exact opposite of independent. They're a chain. And here's the clever part, how he proved it with numbers. First, he just did a simple count. Okay, 43% of the letters are vowels, 57% are consonants. Simple enough. Then he asked, all right, if these were totally random and independent, what are the odds of two vowels showing up back to back? The math says about 18%. But when he actually went and counted in the poem, it was only 6%. Bang! That was the proof. The letters were absolutely undeniably connected. So from this data, he built this simple little predictive engine. He just defined two states. You're either on a vowel or a consonant. And then he calculated the odds of jumping from one state to the next. So for example, if the letter you're on is a vowel, there's only a tiny 13% chance the next one is also a vowel, but a huge 87% chance it's a consonant. He basically created a chain of probabilities.
Okay, and here is the killer blow. This is the brilliant part. He ran his little machine, just generating a new string of letters based only on these dependent chained probabilities. And guess what happened? The new text, this totally artificial sequence of letters, it settled into the exact same ratio, 43% vowels and 57% consonants, a perfect match to the original poem.
He'd done it. He proved, beyond a shadow of a doubt, that you could have a system of totally dependent events that still followed the law of large numbers. This just completely demolished Nekrasov's entire argument about free will. And, being the guy he was, Markov couldn't help but twist the knife a little, ending his paper with his final jab at his rival. And in doing so, he'd accidentally invented something incredible, the Markov chain. So for decades, this Markov chain was just a cool, abstract piece of math theory. Markov himself, honestly, didn't really care about what it could be used for, But what he couldn't have known was that his idea was about to become absolutely essential for one of the most secretive and high-stakes projects in all of human history. Okay, let's fast forward to the Manhattan Project. The scientists had this huge problem. How do you model the chaotic chain reaction of neutrons inside a nuclear bomb? The math was just way too complex to calculate directly. And the solution, believe it or not, started when a mathematician named Stanislav Ulam got sick. He was stuck in bed, bored, so he just played game after game of solitaire. And that got him thinking, hey, what are the actual odds of winning a random game of solitaire? Now, why is that such a hard question? Well, because the number of ways you can shuffle a deck of 52 cards is 52 factorial. That's this number. It has 68 digits. It's a number so mind-bogglingly huge that it's way, way bigger than the number of atoms on our entire planet. So, actually calculating the odds? Forget about it. It's literally impossible.
But then Ulam has this genius idea. He thinks, what if I don't try to calculate it? What if I just simulate it? Just play a few hundred random games on paper and count how many I win to get a pretty good estimate. He tells his colleague, the famous John von Neumann, about this, and a light bulb goes off. Von Neumann realizes this is the solution to their neutron problem. See, a neutron's path is dependent on the neutron that came before it. It's a chain of events. You can't just pick random outcomes. You have to model the chain. What they needed was a Markov chain.
So this whole method, which they called the Monte Carlo method, was a total game changer, born from a card game and an old math feud. But the story doesn't end there. The next giant leap for Markov's idea would come another 50 years later, thanks to a brand new technology that created yet another impossible problem to solve. If you remember the internet in the 90s, you'll know it was the Wild West, a total chaotic mess. Finding anything useful was a nightmare. The first search engines, like Yahoo, were pretty basic. They just ranked pages based on how many times a keyword showed up. And of course, people immediately figured out how to cheat the system. You could just type a word 1,000 times and make the text white so nobody would see it. There was just no way to tell if a page was actually any good or important. And then, these two PhD students at Stanford, Larry Page and Sergey Brin, they have an idea that should sound pretty familiar by now. They thought, what if we model the entire web as one massive Markov chain? Each web page is a state, just like the vowels and consonants in Markov's poem, and all the hyperlinks connecting them, those are the transitions from one state to the next. They basically came up with this idea of a random surfer who just clicks on links all day, forever. The pages that this imaginary surfer ends up visiting the most must be the most important ones, right? They're the most connected. And a link from a really important page, say a big news website, counts as a much stronger vote than a link from some random personal blog. They called this algorithm PageRank, and it became the core technology for their little startup, which they called Google.
So let's just recap for a second. We went from a petty academic feud about free will to helping build the atomic bomb to organizing all of human knowledge on the internet. This one single idea just keeps popping up. So what is it? What makes it so incredibly powerful?
Well, the secret sauce is something called the memoryless property. It's a bit counterintuitive, but for a huge number of really complex systems, it turns out you can basically ignore their entire past history. To make a really good prediction about what's going to happen next, all you need to know is what's happening right now, the current state. This makes ridiculously complicated problems much, much simpler to solve. It's used in everything from the autocorrect on your phone predicting the next word you'll type to, you guessed it, figuring out how to shuffle a deck of cards. Which brings us full circle back to our first question. If you're doing a proper riffle shuffle, the kind you see in casinos, how many times do you have to do it to make the deck truly random? Thanks to Markov chains, we know the exact answer. It's 7, just 7 times.
But what about the way most of us actually shuffle? That clumsy overhand shuffle. Well, to get that same level of randomness, you would need to shuffle that deck more than 2,000 times. Yeah, a pretty huge difference, right?
And I think that really just sums up the incredible journey of this idea. It started as a weapon in a bitter academic feud, a purely theoretical point. And now it's become this fundamental tool we use to make sense of the world. It literally shaped the 20th century, and it's the engine running our digital lives in the 21st. Which leaves you with one really big question. What's next? What seemingly impossible problem will it solve for us tomorrow?